In this lecture, we will talk about pattern recognition circuits. Pattern recognition circuits. What is a pattern recognition circuit? It's a circuit that can recognize the input sequence of binary numbers. For example, I want to have a circuit that has one input X and one like output LED output, and I want my circuit to be able to recognize a pattern of binary numbers. Let's say 1001. So as soon as the input information applied to the circuit is equal to 1001, the output will be set to the 1. So we have a train of inputs that are like binary numbers, and as soon as the circuit recognize the pattern, it will be activate the output. For example, in this sequence of information, we see that this pattern, this like sequence of binary numbers, can be seen at this location. So when we apply this information, one number, first information, second information, third information, so we apply them one by one in order, and as soon as the circuit recognizes the pattern we want, the output will be set to 1. So this one is how a pattern recognition circuit works, and in this lecture we want to learn how to design a circuit which is able to recognize a pattern of numbers, digital numbers or binary values. So we started this discussion by example. So example, design a clocked sequential circuit with JK flip-flop that recognize the input sequence of the input sequence of 1010, including overlapping such that for input X, which is 0010101010111, the corresponding output Z is output Z is equal to, so we looking for 1010. So the first 1010 is here. So as soon as the circuit recognizes this sequence, the output will be 1. So the output is 0000000. So at this moment, which the sequence has been recognized, the output will be 1. Then we continue. The next time that the circuit sees this sequence, it's here. So the output will be 0000, and at this moment output will be 1. The next time that the circuit sees this sequence, because the overlapping is allowed, we know that at this for this 4 period. for these four numbers, we again have the same sequence. So here is 0, here is 1, and 0, 0. So this one is the output of the circuit. And if you look, you see that the circuit has recognized this pattern 3 times, which 2 of them have overlapping. Because the overlapping is allowed based on the problem definition, it's fine. Otherwise, if the problem says that with no overlapping, the last one, the last sequence would not counted as like the pattern because it has overlapping. So this one is the problem and we want to design the circuit. Let me check to make sure that it's a recording. Okay. Now let's go back to our problem and solve it. So we need to start this type of problems with a state diagram. As you remember, when we talked about the design algorithm, I said that the first step is drawing the state diagram based on the word statement of the problem. Okay, so how many states do we have? Let's start from the beginning and see how many states do we need to solve this problem. First state, I will call it state A. What is the state A? It's a state that input is out of sequence. For example, at this moment, not this moment, at this moment, at this not again this moment. Let's just focus on the first part. At this moment, at this 2 moment, when the input is out of sequence, there is nothing recognized yet. So no, none of these 4 bits are recognized. We are out of sequence. So we say state A is input is out of sequence. This one is the first step. So the next state is state B. Okay, what is the first digit that will be recognized in recognizing this sequence? Of course, is this one. This one is the first digit which will be recognized. So we say state B is a state that sequence of 1 is observed. So as soon as the circuit recognizes 1, it moves to state B, because if we look at this sequence, we see that the first digit we're looking for is 1. So what is the state C? I'm sure that you can tell me what is the state B. C. State C is a state that a sequence of 1 0 is observed. So in state C, sequence 1 0 is observed. Okay, do we need one more steps? Of course. What is the state D? Sequence of 1 0 1 is observed. Okay, is observed. Okay, for all these states, the output is still is equal to 0, because it's correct that we recognize part of the sequence but not entire sequence. So still the output of the circuit is 0. One more step, the last step is state E. In state E, sequence of 1 0 1 0 is observed, and of course the output will be 1. So it says that the sequence has been detected. Okay, the sequence has been detected. So we want to work with these states and draw the state diagram. So let's do that. So we say state A, state B, state C, state D, and state E. And now we need to do all the transitions between these states based on this information. So let's say we are in state A. Okay, we start from and we observe 0. Do we move to a state B? Of course, no, because a state B is in a state that 1 is observed. So if we are in a state A and input is 0, it remains in state A and the output is 0. Now, let's say the state is A and 1 is observed. When 1 is observed, we move from a state A to a state B because B is a state that says 1 is observed. So if input is 1, this state changes to B, but still the output is 0. Why the output is 0? Because still not the all sequence, entire sequence has been detected. Now let's say we are in a state B. We are in a state B, so 1 is observed. In order to move to a state C, what data should be observed? We observed 1, so we need to observe 0 to move to a state C. So if the state is in B and 0 is observed, the state changes to C and the output is 0. Now, what if we are in a state B, 1 is observed in a state B, and another 1 is observed again? So we know that 1, 1 is not like this sequence, but we can ignore the first one and say the sequence will be starts from the second one. So again, we'll start from a state B. So just 1, 1 is observed. So if the input is 1, the state will be like state B. There is no state change, and the output is 0. Okay, now we are in a state C. In the state C, 1, 0 is observed. In order to move to a state D, what like bit has to be observed? Of course, 1, 0, 1. So if input is 1, we move from a state D, C to a state D, and the output is 0. Now, if we are in a state C and 0 is observed, what's gonna happen now? 1, 0, 0 is not like in this form of the sequence we're looking for, so we are like completely out of sequence. We are out of sequence. 1, 0, 0. So it can like we cannot fit 1, 0, 1, 0 in this like sequence of data. So we will the system will be out of sequence. So if we are in a state C and 0 is observed, the system will be returned to state A and output is 0. Now we are in a state D. In state D, 1, 0, 1. Let's say 0 is observed. If 0 is observed, it means that we have detected the sequence. So we move to state E. So if 0 are observed, the system moves to state D, and this time the output will be 1 because the sequence is observed. Okay, what if in a state D 1, 0, 1 instead of 0, 1 be observed? So at this situation, because 1 is observed, we will the system will be moved back to state B. Okay, so if we are in state D and 1 is observed, the system will be back to state B and the output is 0. Now let's say the system is in state E. So 1010 is observed and the like overlapping of course is allowed. So what if 0 is observed after that? So we see that 0 0 is completely out of sequence, so the system will be returned to state A. So if 0 is observed, the system will be returned to a state A. Now, what if at a state E, 1 gets observed? So if in state A we observe 1 0 1, so we can consider this part as a sequence, this part. And this one is state C. So we can state D. So we can say that the state will be changed to D. So if 1 is observed, it will be changed to state D. So this one is the entire uh, the entire state diagram. From this state diagram, we want to draw the state table. So it is easy because we have 1, 2, 3, 4, 5 states. So 1, 2, 3, 4, 5 states. X, which is input, 0, 1, state A, B, C, D, E, and of course here is present state. If we are in A, based on this state diagram, we complete the state table. If we are in a state A and the input is 0, so we remain in a state A and the output is 0. And if we are in a state A, input is 1, the state changes to B and the output is 0. So we can complete the entire table. Okay, now that we reach to this point, we have a state table. We have 5 states, so we need 3 flip-flops because um, 2 to the power of n should be greater than greater equal to 5. We're looking for the smallest n. So the smallest n is 3, so we need 3 flip-flop before reduction. So let's go ahead and try to reduce the number of states. I'm not going to do that to reduce this state by partitioning because we don't have time, but if we just inspect, we see that the state C and the state E are equivalent. The state C and the state C and the state E are equivalent, so we can just reduce the number of states if we can remove a state E. So the reduced state table will be this design 0 1 A B C D A 0 B 0 C 0 B 0 A 0 D 0 C 1 B 0. Now the next step is state assignment. State assignment. In the state assignment, we say A is replaced with 0 0, B with 0 1, C with 1 1, and D with 1 0. So the state table will be in this form: 0 0 0 1 1 1 1 0 0 0 0 0 1 0 1 1 0 0 1 0 0 0 0 1 0 0 1 1 1 0 1 0. So this one is the state table, and then we need to design it with two JK flip-flops. So here is first flip-flop, and here is second flip-flop, and here we're going to draw the output. So for the first flip-flop, which is JK flip-flop, so we say J1 K1. So J1 K1 is 0 1 0 0 0 1 1 1 1 0. So based on the excitation table that we know, for a state table, yes. Excuse me. Um, Based on the excitation table for JK flip-flop, we can fill this table. So we start for Y1, which is uh, this zero, this digit, and the first digits inside each cell is for Y1. And if we complete and fill the table with excitation table of JK flip-flop, we will have 0D, 0D, 1D, 0D, D1, D0, D0, D1. This one is for J1 K1, and the next one is for J2 K2. So it will be by using the excitation table. We will have 0D, 1D, D0, D0, D1, D1, 1D, 1D. This one is J2 K2, and the output is 0 0 0 0 0 0 1 0. So this one is Z. So which we can immediately write the function, which is x bar y1 y2 bar. This one is the excitation table. So each of these tables can be expanded, split to two tables for J and K. So we move for J1, another table for K1, like here again for J2, and K2. Okay, so we just insert the first digit of these cells to J1 table, the second digits to K1, the first digits of the second table to this table, and the second digits of second table to this table, and we will have 0, 1, 1, 0, DD, DD for J1, DD, DD, 1, 0, 0, 1 for K1, 0, 1, DD, DD, 1, 1 for J2, and DD, 0, 0, 1, 1, DD for K2. Now we need to simplify these functions. So for J1 we can group these two, and of course oh, let me look here. Oh, this one for the first table, it should be, I'm talking about this part. It should be 0, not 1. If we look to this table, 0, 1, dd, 0, 0, dd. Yeah, it's 0, 0. Okay, it's 0, 0. So J1 is here, which is x bar y2. For K1, we can group them in this these two together, and this one with this d. So we will have K1 is equal to x bar y2 plus x y2 bar, which is x or y2. So this one is K2. For J, K, this one is K1, sorry, not K2. For J2, we group these four together, and of course we group these four together, and J2 will be equal to y1 plus x, y1 plus x, and the last table, we can group these four together, and K2 will be equal to y1. Okay, now that we have all these equations and the output equation, like the last example, we can easily draw the circuit. Okay, in the next lecture I will do another example.